Hello everyone, I'm Suraj. This is the term paper presentation for PHY 402 course in solid state physics, and the topic for my term paper was superfluids. So the idea of giving this presentation is the purpose is to uh, show the concepts in a more intuitive manner and not show too many equations and stuff. Okay, so next, this is a cup of coffee filled with normal fluid. It has all the not so nice properties of fluids that we don't know how to work with. Like if you stir it up, you'll see that after some time it stops, and due to viscosity, it has friction and it undergoes scattering with the walls of the cup and all those things that we don't like. And next, we have superfluid helium in a container. We see that if we put it in a container, after some time it starts uh, going over the top of the walls of the container, and it will also leak down to the bottom. And why are these things there? Why does it like why does a superfluid have all these properties? The answer is simple: zero viscosity. And why is that so? That I'll try to explain in the next few slides. So first we go through bosons. Basically, there are two kinds of fundamental particles in nature: bosons and fermions. Bosons like to stay in the same quantum state, while fermions don't like each other. They only stay with other fermion if it has opposite quantum state. Like if one fermion has spin up and the other has spin down, they both can stay in the same quantum state. Otherwise, they can't stay in the same quantum state. Whereas bosons, if like in the next slide, I have this wave function. Let us say you have n tends to infinity in this. What this wave function says is firstly that psi n is the wave function, is a wave function to have the, so that all the n particles are in the same quantum state. If I add to n minus one particles, if I add another particle, then whether the this particle would go to same quantum state as the other n minus one particles, the the wave function for that is under root n into n minus 1. So you can see, if we say that n is a very large number, and we try to find the probability of whether this new nth particle would go to the same quantum state or a different quantum state. In that case, we'll find that most probably uh, the the new boson would go to the same quantum state as other n minus 1 bosons, and the probability to go in a different state would be diminishingly low as n goes to infinity. And why is that so? So you can see that bosons already have a very interesting property, and these properties don't show up in normal every today life, because other effects overcome these energies very easily. But let's say if we can have these bosons at a very low temperature where they can show these phenomena easily, then these would give rise to very interesting phenomena, and that's what we're going to study in the next few slides. So next we have Bose-Einstein statistics. This is the function for Bose-Einstein statistics. But what this function basically says is that uh, the probability to have nth particle in a state with energy ek, and when the chemical potential is mu, is given by this particular function 1 by this fraction. And if let us say we have mu equals to 0 for due to some conditions, and then we have this function is capital N, that is total number of particles is equal to sigma k 1 by e bar beta e epsilon k minus 1. And now let's say we have epsilon very low. Let's say epsilon goes to 0 for some state, then we'll see that this function would shoot up for that particular k value, right? So this you can see that what is going on is, now in practical life we don't have this epsilon k going to 0, because we have vacuum. There is a minimum energy is quantized, so there is a minimum energy h bar omega by 2 for these states. And but even then, when epsilon k is very low, you can see that most of the particles would be in the 0 k equals to 0 state, and not in, and the particles in the other states would be very low. So at small temperatures, a macroscopic number of particles are in the zero momentum state, that I already said, explained why. And next is we want to study helium. So why helium? Helium has some certain properties which I have explained in the paper as to why helium forms a liquid even at zero, almost at zero Kelvin temperature also. And in this presentation, I'll show He4. 4He is a boson, while 3He is not. So you see that 4He forms a Bose-Einstein condensate or a superfluid at almost 2 Kelvin temperature, while 3He it's a fermion. So for it to form a superfluid, you'll have to go to almost 3 orders of magnitude smaller temperature, which is almost like zero point zero 0.00 something Kelvin. So and even then it has to form Cooper pairs, which uh, something analogous to Cooper pairs, which we found in superconductivity. So next is 4H is a weakly interacting Bose gas. Before this, I should say that Bose-Einstein condensate is Bose-Einstein condensate consists of particles which don't interact with each other. So it's a gaseous superfluid kind of state, Bose-Einstein condensate, and 4He it interacts, but it interacts weakly with itself. So now you can see that for the same properties, it shows same properties at Bose BEC, but what happen is that the particle density which tending to when for smaller temperatures when particle density was tending to zero, sorry, not particle density but condensate density. As for the diminishingly low temperature for a Bose-Einstein condensate, the uh, condensate density was tending to the total particle density. But what happens here is we calculate through quantum Monte Carlo simulations that and it can also be verified by the pressure distributions that can be observed in a experiment, that for a 4He, not all condensate density tends to be constant n0 instead of the total number of instead the total density. So where the rest of the stuff go, it goes to a higher excited state, or yes, which then forms the normal component of the superfluid, which we'll talk about later. So this is the graph showing the same thing that I said just now. Now, since all these particles are bosons, they form a single quantum state and move in a unison, or so we can talk about this particular macroscopic wave function which defines the states of all the particles and all the particles in the same quantum state. But here in this particular equation number one, you can see that the psi 0 has a n naught factor and I theta r factor. This n naught factor says that the particular condensate density of the superfluid, and I of theta r say what is it is it is a it can be it is a degree of freedom associated with each particle r, each point r in the space. And what that is that you can see that it's like a degree of freedom associated with each particular point in space. It can take any value, and what this particular AFI theta r factor is just a very interesting phenomena which I'll talk about now. So we have next we can define a velocity, the derivation of which I have done in the term paper. The velocity can be defined by the gradient of this theta factor at each. So this has a nice consequence that the curl of v is equal to 0, which implies if we talk about circulation, which is the integration of this velocity factor over any closed loop in the superfluid, you'll see that this is quantized now. So this what this is the flow is irrotational. Now what we can do is if we put a let's say if we put a superfluid in a cylinder and rotate it, what we see is that the free surface, it shows properties like that of normal fluid, like with the walls its level rises with the walls. And but what is happening, because we talked about the flow should be irrotational here, right? So the paradox, this is solved by uh, talking about vortices or introducing vortices. What a vortices is, vortices are small local, you can say small local bodies of rotation, and their rotation is quantized. That means that uh, rotation is constant, then mostly you will find these vortices in the rotations of in the quanta of +1 and -1. If it is in a quanta of if it is in a higher energy level, it mostly splits into smaller energy levels, and mostly these occur in pairs. We have some vortex lines also, which uh, but one effect of these vortices that would I would like to highlight here is that they destroy superflow. How do they destroy superflow? Is because you talked about superflow can't rotate, and the flow is irrotational for a superflow. But we see that there are vortices. So what is going on here? The answer to that is that we have normal fluid component in the superfluid. That is, they contain a normal fluid component. How come there is a normal fluid component? Because only at t equal to 0 we have a pure superfluid. At anyway, if t is even at below lambda point, if t is below lambda point, we always have a finite. If t is not equal to 0 and we are below lambda point, there is a finite amount of normal component density. That is, all fluid is not converted into superfluid. There is some fluid that we can in this model only, that there is some fluid that is not converted into superfluid, and it gets converted if the temperature goes to 0. And this is the total current is given by the superfluid current and the normal current. These can be added, but one should always keep in mind that this is just a model. One should not take it physically, because there are no, it's not like there are particles, some specific particles which belong to a superfluid component and some other belong to a normal component. And a very nice thing that uh, we have, uh, Landau gave an explanation of this. Actually, Landau didn't give an explanation. It was just that by Landau's model, we can explain what this normal fluid component and superfluid component are. At least have an idea. So Landau thought about that uh, when a superfluid goes through a capillary, there is no viscosity. That means no scattering is happening with the particles of the holes. Why is that so? Because in a superfluid we have all the particles in one. They move in a unison. They all have one particular one quantum state. So if we want to change the energy state of one particular particle will have to change the energy states of all the particles simultaneously, and that's not possible for uh, and that the probability of that happening is very low. And that this thing is true for a particular region of velocity in the graph. As you can see in the dispersion graph, there is a linear curve. This particular curve also resembles the phonon part in the solid crystals. And this particular thing, this is the superfluid component, as one can see. And we have a maxima. After that there is a minima, and this minima part, this behaves like a normal fluid component. This is called the roten part, and I've talked about this in the paper. And thank you for